start. Welcome
Okay.
you all back to statistical methods in finance. This is the fourth session, and this is an invited session. There are two speakers, Professor Yoann Potiron. I hope I have not mispronounced your name. He's from Kyoto University, Tokyo. He's going to talk about tale of two time skills, applications in non-parametric Hawkes process with Ito semi-martingale baseline. Professor Yoann, the stage is yours.
Okay. Thank you very much for the introduction, and thank you very much for the invitation. I also I have never been to India. I wish I was there, but still I'm happy to remotely give this talk. Currently, I'm in France actually. So this is a joint work with my students, Songshu Yo, which is actually a student in Korea. So in a different, in a different university, because I'm in Japan, but it's we're remotely working together. So the takeout is that we build a general machinery with several applications. So this is more like we provide like a general, I would say, theory. So it's more like theory-oriented paper, even though we have applications and as well as empirical, some numerical studies and empirical work. So basically, this can be. Yes. Can you hear me? Still hear me or?
Yeah, we can hear you.
Okay, yeah, I had like some noise. Yeah, so what we're in like financial econometrics, and so essentially what we're doing is we're building Hawkes processes. I'm gonna get back on what it is. So we're modeling point process, arrival times with like Ito semimartingale, so time varying baseline. And then by using some TSRV, two scales realized volatility method, which is probably the most popular method to estimate volatility with high frequency in high frequency econometrics. We're using this kind of methods to actually work on the point process itself rather than for estimating volatility. And then we have a bunch of applications on that. So as I was mentioning, central to understanding the economics is the information collected with high frequency transaction time. So we're thinking about one day of horizon, like from 8:30 to 5 p.m., just one day of trading. So it could be 100,000 points, if it's a highly traded stock. So it could be like 5,000 points over one day window. And the examples of applications that we have are like credit default risk, portfolio choice, financial contagion, low latency measure, and so on. So there's a lot of applications to, related to those arrival times. And what happens is often in the literature, we tend to think of regular arrival times. So if you take a day of trading, most of the papers are, a lot of papers will assume that the arrival times, the times of trades, they are regular. So let's say every 1 second, every 1 millisecond or so, which of course is not true in practice, because in practice, the trading times is actually, chosen by the trader or the broker itself. So it's actually random. Okay, so we're in this family thinking that the point process, we believe in like in a point as a random process. And so, we're trying to build that. I mean, based on the literature. So essentially, the main stylized facts that we have on financial high frequency data is the so-called like time clustering. If one observation, if there is one trade, then the likelihood of the next trade is increasing. This is what it means, time clustering. So if you observe one trade, there's there's a tendency that people are going to trade, or algorithms are going to trade more actively after this trade. And so this is well-known time clustering effect. And there are two more, popular approaches to model arrival times and taking care of this time clustering effect. There is a discrete approach called the autoregressive conditional duration model, the ACD model, from Engel and Russell. And there's also a continuous framework, Hawkes processes, or so-called self-exciting processes. So both approaches are very close to each other, but they are different, So I suggest we look at them before, making so this is the ACD model. So this is defined via its Hazer function. So the DI corresponds to the if duration. So the TIs are the arrival times, so T0 is just 0, and then T1 is the first time there's a trade, and so on, T2, T3. And so the if duration is DI equals TI minus T1. And so there is this ACD model where essentially what's important is that we're modeling, there's an expectation missing actually. We are modeling the, so that's CI equals expectation. So conditional expectation of DI, knowing the filtration up to I, to time I, and the theta. So this is a, parametric approach actually, and also discrete. And so the main thing is like in this ACD model, we kind of define this conditional expectation in the model. And the other approach is the Hawkes processes. So if we define the number of market events up to T as capital NT, and then its corresponding intensity as lambda T, what is the intensity is like it's kind of the average, the expected average of observations, So if in this Hawkes process, this is lambda T, the intensity equals mu plus this integrated exciting kernel function, and the mu is just the Poisson background. So in the case where the excited kernel equals 0, we are just into the Poisson process, okay? And so there is no Hawkes if phi equals 0, if the exciting kernel equals 0, then we are in the Poisson process. And so these Hawkes processes, they're very popular, maybe not as popular as the ACD, but they have been successfully applied in finance. And this is just, you know, a small fraction of the kind of work you can find on, I would say, Hawkes processes, you know, related to, or finance-related Hawkes processes. There's also even at least two reviews on the use of Hawkes processes in finance. So it's a main, it's been recent, but, you know, it's out here. So, you know, those two methods, they're doing a good job for time clustering. But now we all know that, I mean, we all know. Now I'm going to discuss the other, you know, stylized facts. Stylized facts. So the second main stylized fact is seasonality. So this seasonality is like, you know, you can see this, you know, kind of like starting from here and then you go. So it's kind of like, you know, it's one day. This corresponds to one day. So you usually see like kind of like an inverse J shape. So this is, you know, well known as seasonality. You know, that's. And now what's interesting is that ACD method is actually not robust to seasonality. And as far as we know, there is no seasonality robust ACD related extensions out there. You know, despite the fact that the seasonality has been well known way back, there is, as far as we know, no formal ACD related paper. As for Hawkes processes, usually they assume a constant background. So what is the background? This is the mu here. So usually in Hawkes processes, they assume this mu is constant. And therefore, with assuming this kind of constancy, we cannot observe seasonality. So this is also well known in Hawkes literature that, you know, there is this kind of inverse J shape or seasonality. And so there is a few exceptions to papers with a time-varying background in the Hawkes literature. And Chen and Hall consider a parametric Hawkes process with time-varying background. And Simon Kleine and myself develop a stochastic time-varying parameter Hawkes process, but with exponential kernel. Beyond those two examples, we can see, you know, with the examples, with we can see this seasonality, you know, and that we can see that it seems that the baseline is time varying in those two, although they're, you know, so knowing that there is this works and Hawkes processes, it seems that the Hawkes processes would be more amenable than in ACD model to incorporate seasonality. So now I'm adding a little bit of but additional stylized facts, which are also, you know, part of the literature. So the first one is stochasticity. So we had this seasonality, but, you know, there is this inverse J shape for one day, you know, and maybe when we discuss stochasticity, we mean that from one day to the next, it won't follow this deterministic pattern. I mean, you can see it, you know, it looks stochastic, right? So there's kind of like a day-to-day effect, stochastic effect. So you would kind of like want a model where the baseline would follow also the stochasticity, and then you can see those bursts. You can see here. This is here the most prominent burst. There's a literature on that relating bursts to macroeconometric news and so on. And volatility also jumps. So, it has to be incorporated too, those two empirical. So it means that we want a model which incorporate 4 stylized facts versus the ACD and the current Hawkes process, which just incorporate 1 fact, 1 stylized fact, like the time clustering effect. So the model is that we consider is infill asymptotics. The infill asymptotics is just the number of observations explodes on a compact set. And so we are basically observing from 0 to T, capital T, which is the horizon time. So typically 1 day of trading. So, capital T, just the end of the day of trading. And so this is the kind of, so this N is for the, I would say scaling parameter, so like the asymptotic parameter. And this is the model we are, so what's important, what's the difference between our model and the Hawkes model is just that we have this time varying T in mu. So this is what we're doing. We're putting a time varying baseline Hawkes process. So for the time varying baseline, we consider an Ito semi-martingale baseline. So just like this is the drift part, and this is the martingale part or Brownian part, and these are the jumps. So in practice, this means those jumps kind of help for this intensity bursts. Sorry, and this one plays the role of kind of like stochasticity, and these drifts can be random, but if we put a deterministic part into it, then we also have, so we can incorporate seasonality. So we can put a like a deterministic drift for seasonality, and then the rest is just for the 3rd and 4th stylized fact. And so now we're providing the main result, which is just a local estimation of Poisson, I would say the local of Poisson estimates, together with this like kind of realized volatility. So realized volatility is kind of like we're estimating variance, variance of the local estimates, and we, because there are jumps, we're using this truncated term. So this definition of just like this is the average mean. So essentially, NT is just, we're estimating the mean with just the number of observation between 0 and capital T. And then we're estimating the kind of like the realized volatility of it has the sum of the difference. So just the local number of observations on each block squared, Okay. So the target values are just, the mean is just the integrated baseline. You know, there are some scaling parameter, and also you see this quantity, which is related to the Hawkes. So this is what we call the branching ratio. So the, like here, this is the branching ratio. And then the realized volatility is just defined as this. So more or less like kind of a variance of the Poisson estimates. And then we have a bunch of assumptions on baseline, and nothing is so. Yeah, the branching ratio is strictly less than 1. This is, the B is just for stationarity of Hawkes processes. And then we also need this short range condition. So we kind of need a little bit more on this kernel, but this doesn't rule out power law kernel, because in the Hawkes literature, the exciting kernel has been shown to be more like power law decay. So this kind of behavior, it is nested in our resumption. Okay. And then, we need some like finite value. So no, like just, usual kind of assumptions. And so then we provide like the central limit, the main CLT, which, so this is, you see there is CLT. So this is giant CLT, and this is on mean. This is one scale of realized volatility, and this is another scale of realized volatility. And the reason why we need those two scales is to, for applications, by taking, linear combinations of those two, we can estimate the whole kind of quantities. So this is really important. So this is the main title comes from here, TSRV. We need those two. We need a joint with two different scales. Without those, we are not able to make the applications. Okay, so this is very important. This is what made the title of this paper a tale of two time scales. So we're looking at this, and then we obtain this asymptotic variance. There's nothing to say. And we have like a feasible version of the CLT, and we've just like the asymptotic variance. So everything is, estimable. So yeah. So now we are providing the main application. Surely we're providing several applications, but first, like this is branching ratio estimation. Then we're going to discuss other applications, and the main is, I think, is branching ratio. So the branching ratio is, it's defined as the integrated, integrated kernel. So first, I'd like to emphasize on the fact that we are already assuming that it should be smaller, strictly smaller than 1. Because without this, we cannot. This comes from Hawkes process stationary requirements. So this branching ratio is this quantity. And we know this is between 0. It can be equal to 0. If it equals 0, we're back in a Poisson process. So no Hawkes component. And if it's close to 1, then it means that people kind of call like full endogeneity or criticality, So this branching ratio can be seen as a measure of the degree of endogeneity, and it's actually the average proportion of endogenous events on financial markets. So it's out there. It's been, there's a lot of literature on that. A lot of literature to estimate this, and a lot of empirical work on, some kind of debate on, how close we are from full endogeneity. There are a group of researchers which find that this branching ratio is very close to 1, and, a different group of authors would argue that this branching ratio is more around 0.8, and that the other methods, so the methods from the group which find almost endogeneity, they're kind of arguing that their methods is biased. In this paper, where we kind of like take this position that, we're kind of like trying to understand this, actually, trying to understand if branching ratio, what we find empirically with branching ratio. So this direct non-parametric estimator, which is highly used, is defined simply as you just need the empirical mean and the empirical variance. And this is this, Hardiman and Busho estimator, or Hardiman-Busho estimator. And, when the baseline is time varying, there is a poor bias. And so we will show you this on numerical simulations. And this was also pointed out by different authors, So to update the estimator, we propose to replace the variance estimator by our TSRV estimator, Again, this TSRV is just, as I said before, a linear combination of the two scales of realized volatility. So this is a real TSRV, And this leads to our branching ratio estimator, which is just the same as Hardiman-Busho, except that now we have a time-varying baseline robust TSRV estimator on the denominator. So, and so what they provided was just consistency of their estimator, and we're providing a little bit more because we actually, as just the corollary of our work of this general central limit theorem, we have this branching ratio CLT, and again, it's feasible, works well in practice, so it's nothing, Now I can discuss different kind of estimations. So another estimator that we're interested in is like the integrated intensity. So, in practice, traders should be interested in that because, this is kind of like the expected total number of a transaction, on like, let's say a day, So just like, integrated volatility, now it's integrated intensity. So there is a lot of work. There is the Slimish work, 1991, but they're all so estimating this integrated intensity, but they're all in Cox process model. So in the case when the exciting kernel is equal to 0, and also their asymptotic is different. They're considering not infill asymptotics, but more you know, observation of different point processes, you know. So uh, you know, so in the case of our paper, we update this integrated intensity by expectation of the integrated intensity given the baseline. This is just, you know, because we have a time varying baseline, this is you know, this is the way you know, we're thinking it's better to consider this. And if the baseline is actually constant, then this expected is equal to the integrated intensity. And then we have like a CLT again, two CLTs actually. In the Cox case, so the Cox again is like when the integrated, the exciting kernel is equal to 0. The Hawkes case is when the general case is not equal to 0. And there's this algorithm which I won't discuss. And another application is the integrated volatility of the baseline, you know. And again, when there is no Hawkes processes, there is this Kimura and Yoshida work and Stoltenberg and Miklin and Zeng, who, you know, are providing kind of like general machinery also, but they're not providing general, you know, kind of CLTs. So we don't know from their work, you know, actually, we don't know the asymptotic variance from their work. And of course, they do not have a Hawkes component. So we are kind of like providing, it's like, you know, different from like, it's a little bit different from their work. So, and then we have this estimator and again, like CLT, feasible statistics all works well. And now we're providing other applications which are now in hypothesis testing. So for a branching ratio level, you know, maybe 0.8, where one says, is this equal to 0.8 or is this different? And if in the case when C equals 0, it's actually, we're testing for the absence of Hawkes component against the presence of Hawkes component. And so we're providing this, you know, test statistics, this SC, again, corollary from our work. And so, you know, we're essentially providing consistency of this test in now a different kind of test is when actually we're testing for near criticality. So what is near criticality? It is when the branching ratio. So remember, the branching ratio has to be smaller than 1. Otherwise, the Hawkes process cannot be stationary. And so in this case, we're assuming that it tends to 1, you know. And this is what, you know, Gisson and Rosenbaum and a lot of other work, more recent work, they, you know, they found like the CIR process as a limit of what they call this nearly unstable Hawkes process. And so we are testing for this criticality, and the alternative is like no near criticality. So, and this again, like we provide consistency of this. Now another application is time varying baseline test. Again, this is new. I don't even know any other work where there is formal time varying baseline test. So here we just use the fact that this branching ratio from Hardiman and Busho estimator is efficient but not robust, and then that our own estimator is robust but not efficient. And so in this situation, we can think of the Houseman test. And again, we're providing this, again, like limit theory of this application. And now the last application is we are testing the presence of, or the existence of Brownian diffusion term in the baseline. So again, I do not know, I'm not aware of any work doing any related, kind of test. And so again, like this all works theoretically. So now I'm just giving you a little bit of the simulation work that we've done. So we're taking all those values to just be as realistic as possible, and while being a part of our, framework, theoretical framework. And so if you look at one simulated intensity plot for our most general model, you can see on the left pile that there is kind of this J shape, there is this stochasticity, and there are those bursts. And if you look at the third, on the right panel, then right panel is just the real data intensity. Okay, so again, those are really close. We tuned those parameters to fit the data as much as possible. Okay, so a little, we're providing a bunch of models, no Hawkes, Hawkes exponential, Hawkes power, and nearly unstable Hawkes process. And, we're, putting the burst CIR process. And so again, as realistic as possible. So this is one example of the limits QQ plots, and like this is 5% level for this is okay. This were the results of the branching ratio estimator. We've also done this kind of work for the other estimators, for integrated intensity and integrated volatility estimators, but we're not providing this in this talk, but they're available on our working paper. And so the power behaving, you can see as n increases, the size are around 0.05, and this is 5% level, and then the power is around 1. So, and this is the Hawkes test. This is the near criticality test, the time varying baseline test, and the Brownian baseline. Yeah. So they're harder to. So the Brownian baseline test is it's a little bit, harder to use in practice, because you can see it's not as close, and the power also is, it takes time to so it takes a lot of n, so it's harder to see on empirical application. And then we're comparing our method with, so our branching ratio method with a bunch of with a range of different, several other estimators from the literature, including this Hardiman-Busho with different window, and then MLE exponential, and this EM algorithm. And so as you can see, in case of model 4, so yeah, in case of model 4, there's not just us, who's working well. So because in model 4, I think if we go back to the models, yeah, there's Hawkes, but we have a constant baseline. So in model 4, because the baseline is constant, we shouldn't be actually better than the other estimators. They're all consistent, but probably some of the others have a better variance than us, so they beat us. But as soon as you put time varying, as soon as you put a time varying component here in model 6, then we're still on top of things. But the other methods, they're upward biased as expected. And when we put even more, I would say, closer to the world kind of model. No, this one is when so model 3. Let me get back to. So model 3 is like when we are also putting burst and CIR and J shape, but no Hawkes. Yeah. So we obtain this results that the other methods are highly biased. When the true branching ratio is around 0, so again, there's no Hawkes. So the true branching ratio is 0. We're estimating quite well, but all the other methods are actually close to 1. So again, there's 3 minutes left for the empirical study. So 20 years data. So what we do is that we have this flash crash and we have this COVID-19 crash. And, we chose those two crises for a specific reason, because in the flash crash crisis, we believe that that the branching ratio should be close to 1 at the moment there is a crash, or at least it should be increasing, because this is due to endogeneity of financial markets. On the other hand, during the COVID-19 crash, we do not believe this should be endogeneity. So we believe that the branching ratio shouldn't be increasing, during at the moment of COVID-19 crash. And we want to test what we look at this empirical experiment, not experiment, just an empirical data. And so you can see on the left that this is the flash crash. And at the flash crash, as expected, our estimator is increasing, already the ML is going the other way, but Hardiman and Bushel also increase, so as expected. And it seems there is a what we would call this bias, and then there is the EM, which is just close to 1. And during the COVID-19 crash, just when there is this, when it arrives, like the branching ratio doesn't move as expected with one method, whereas it goes down, with this branching with this Hardiman-Bushel estimator. Oh, sorry, it goes first up and then down. So it seems a little bit, affected by. It seems our estimator, as expected, seems more reliable on empirical data, because you wouldn't expect the branching ratio is moving during the COVID-19 crash. And then those are the test results. So I have 1 minute to discuss those test results. So essentially, the global picture is on the left. You have the branching ratio yearly average And so we are around 0.6 now in 2020, 0.6 to 0.7 for us. And you see the other methods not too, slightly upward bias, not, not too badly, I would say. There's nothing to be really too, bad about it. And then there is this Hardiman-Bouchot, which is a little bit more biased from our perspective, and then this are on the right panel, the results of our test procedures. And what's important is that we're almost rejecting all the time. So there is a Hawkes component, so almost 0.1, so, and then the time varying test, it seems that 90% of the time we're in favor, or 95% of the time it seems there is time varying. For the Brownian effect, maybe only 20% of the time. But again, this test is hard to, we saw on numerical studies that it's hard to see. And then yeah, so this is what we have. So yeah, essentially nothing more to say. So thank you. Any questions? Thank you again for this.
Thank you, Professor Yoann.
Thank you.
Any questions?
I have one question.
Yes.
That, a question not about your work, but in general for Hawkes process.
Yes.
See, I mean, here is this functional parameter phi, and that is, considered to be exponential or power function something, and basically it is not. It is fully supported, like on the whole positive real line, right? So, I mean, that basically says that every time influence of very long past is still present of the process, right?
Yes. So you're saying that, I'm not sure what you said. So you're saying that what we know is that the Hawkes exciting kernel is not exponentially distributed.
If no, I mean not extreme. I mean, what I'm saying is that kernel phi has full support. Like the function phi is positive on the full positive real line.
Oh yes, yes.
So that essentially means that at any time t, the Hawkes process has influence of very long past.
Yes, exactly.
Which is quite counterintuitive. Of course, I mean that phi is also decaying, and then that influence is actually very less, but still it is present, right?
Yeah, so I have two things to say about this. I completely agree with your comments, and in terms of how theoretically we can deal with this, support, I would say like this is assumption C. So because we're assuming that the exciting kernel satisfies this short range condition, even though the support can be, up to plus infinity, then we can still deal in the proof by using this. So this is heavily used in the proof, this assumption C. Okay. And second point, in practice, actually, we only have like a finite amount of time, So in practice, it's impossible to respond to the question of, is this, of course, the support, we cannot respond to is the support really goes to plus infinity, because we are limited by the amount of data we have. I hope this makes sense to you.
Sure, yeah. So this this assumption C is basically saying that phi decays much faster.
Yes, exactly. Yes.
Okay.
Yes, so it's a good question. Thank you very much.
Any other question for Professor Yoann? I have one question. So I was just wondering this the central limit theorem that you proved. Do you have any sense of what is, I mean, the rate of convergence, or like how many samples you need to have a reasonable approximation of the normality?
Yes, so essentially these rates are, you know, here. So, you know, essentially this is to, so let's say on one applications on the branching ratio. Yeah, so for the branching ratio, so this is just delta n to the power minus over 2. So delta n is just the size of one block. So essentially, we're taking equally blocks. So capital T is the horizon time. So delta T is of the order capital T over the number of n. So delta n is of the order 1 over n. So, you know, this means that this is of the order, the standard deviation is of the order square root of n, if I'm not mistaken.
Okay.
So I don't think it's especially, you know, it's especially slow. And, you know, remember, this is high frequency financial data. So in practice, you know, like I'm showing, we can have like up to 100,000 observations. Like this one, yeah, this was, you know, we have 150,000 observations, and there was no, you know, problem. Of course, some days where, you know, on not very highly traded stocks, we've just like maybe 5,000 observations, then this becomes a little bit more skewed, you know. So that would probably require like finite sample adjustments. So it's a very good question. Thank you.
Thank you. Thank you. Any other question for Professor Yoann? If not, let's give a thanks to Professor Yoann.